Today we can learn about continuity equation. Continuity equation means it is the equation which is based on the principle of conservation of mass. Continuity equation means it is the equation which is based on the principle of conservation of mass. So you consider a pipe. Now you consider a pipe. All of you see the figure. You consider a pipe. The pipe has two sections, that is we can take section 1 and section 2. Let us consider two sections, section 1 and section 2. Now you can see the direction of flow. The arrow represents the direction of flow. Let V1 be the velocity at section 1 and rho1 be the density at section 1. Let V1 be the velocity at section 1 and rho1 be the density at section 1. And let us assume the area of pipe at section 1 as A1. So, taking section 1, the velocity there is assumed as V1, density there is assumed as rho1, and area assumed as A1. So, V1 for velocity, rho1 for density, and A1 for area. Then coming over to section 2, let us assume V2 as the velocity at section 2, rho2 as the density at section 2, and A2 as the area of pipe at section 2. That is, here velocity V1, density rho1, area A1. Coming over this section, velocity V2, density rho2, and area A2. Now, according to the law of conservation of mass, according to the law of conservation of mass, we may write, according to the law of conservation of mass, we may write mass of fluid at section 1 is equal to mass of fluid at section 2. That is, according to the law of conservation, we can write mass of fluid at section 1 is equal to mass of fluid at section 2. So, we may represent mass of fluid at section 1 as rho1, A1, V1 because rho1 is the density, A1 is the area and V1 is the velocity. That is equal to rho2, A2, V2 because rho2 is the density, A2 is the area and V2 is the velocity. As in it as equation 1. This is how we can represent the continuity equation. Then I have told you about incompressible fluids. For incompressible fluids, the density is constant. That is, rho1 will be equal to rho2. Incompressible fluid ആണെങ്കിൽ density constant ആയിരിക്കും. So what happens? Rho1 will be equal to rho2. So for incompressible flow, the term rho get cancelled. So for them, we may write A1 V1 is equal to A2 V2. In case of incompressible fluids, the density is equal. So we may write A1 V1 is equal to A2 V2. This is how we can represent the continuity equation in a simplest manner. Okay, but we have to learn how to derive the continuity equation in 3 dimension. It is very important. So we can move to that portion. You see continuity equation in 3 dimensions. All of you see the figure. Please see all the components. Please understand them. See each and every point, that is A, B, C, D, not every components. Now, you are considering a fluid element. All of you listen very carefully. This is a tough portion, but it's very important. Okay. So, you are considering a fluid element of length dx, dy and dz. You are considering a fluid element of length dx, dy and dz. Okay, the length of the fluid elements are dx, dy and dz in x, y and z direction respectively. I told you, you are deriving continuity equation in 3 dimensions. Okay, so the length of the component, length of the element in the x direction is dx, in y direction that you can see 3 direction, x direction, y direction and z direction. So the length of the fluid element in x direction is dx, in y direction is dy and in z direction is dz. Okay, is that clear? The length of the components, the length of the fluid element in x direction, y direction and z direction are dx, dy and dz respectively. Next, you can see u, v and w. You can see u, v and w. Now all of you know the direction of u as well as v and w. You can see u, v and w are the velocity components which are acting in x, y and z direction respectively. All of you see u is acting along x direction, that is u is the velocity component in x direction and v is the velocity component in y direction and z is the velocity component in and w is the velocity component in z direction. u, v and w എന്ന് പറയുന്ന velocity components ആണ്. u is acting along x direction, v is acting along y direction and w is acting along z direction. Now we have to find the mass of the fluid entering the phase ABCD per second. We have to find the mass of the fluid entering ABCD per second. So the mass of fluid entering the phase ABCD per second can be written as equal to rho into velocity in x direction into area of ABCD. That is, the mass of the fluid entering the phase ABCD per second. The mass of the fluid entering the phase ABCD per second can be written as equal to rho into velocity in x direction into area of ABCD. You see here, the mass of fluid entering the phase ABCD per second can be written as rho AV. Rho AV എന്ന് നേരത്തെ എഴുതിയില്ലേ, rho 1 A1 V1 എന്ന് just before I have explained it is rho 1 A1 V1 എന്ന് എഴുതാമെന്ന് പറഞ്ഞിട്ടുണ്ട്. The mass of the fluid can be represented as rho 1 A1 V1. So ആ സെയിം തന്നെ ഇങ്ങോട്ട് എഴുതാണ്. It can be represented as rho into velocity in x direction because you see we are first considering x direction. ആദ്യം x direction ആണ് consider ചെയ്യുന്നത്. So the mass of fluid entering A, B, C, D. The mass of the fluid entering A, B, C, D can be written as, per second can be written as rho AV. നേരത്തെ ഞാൻ explain ചെയ്തപ്പോൾ പറഞ്ഞു mass can be written as rho 1 A1 V1. So similarly, a same step തന്നെയാണിത്. That is, mass of the fluid entering the phase ABCD per second can be written as rho into velocity in x direction into area of ABCD, because ABCD എന്ന് പറയുന്ന ഫേസ് ആണ് കൺസിഡർ ചെയ്യുന്നത്. സോ ഏരിയ ഓഫ് ABCD, സിമിലർലി ഏത് ഫേസ് ആണോ കൺസിഡർ ചെയ്യുന്ന അവിടുത്തെ ഏരിയ തന്നെ ചൂസ് ചെയ്യണം. സോ ഏരിയ ഓഫ് ABCD, what will be the area of ABCD? ABCD, the area of ABCD will be, you can see this component is dy and this component is dz. നിങ്ങൾ അത് ഏത് കമ്പോണൻസ് ആണ് നോക്കുക. ABCD, you can see this is dy and this is dz. So area എന്തായിരിക്കും? Area becomes dy into dz. The area of ABCD becomes dy into dz. Then what is the velocity in x direction assumed? The velocity in x direction is assumed as u. Once more, ഞാൻ പറഞ്ഞു, mass of the fluid can be represented as rho into A into V. Similarly, coming over to the 3 dimensions, we are writing mass of the fluid entering the phase ABCD per second can be again written as rho into A into V. The same step. Okay. Now, what is the velocity in x direction? We have already assumed the velocity in x direction as u, velocity in y direction as v, and the velocity component in z direction as w. So, the mass of the fluid entering the phase ABCD will be equal to rho into V into A, that is rho into U into area. Then you consider phase ABCD, ABCD, you consider ABCD, ABCD. This is dy and this is dz. So the area will be dy dz. Okay, the area of ABCD will be dy into dz. You see, this is dy. Here you can see it is dy. Then this is dz. So here you can see it is dz. So what happens? The mass of the fluid entering the phase ABCD will be rho into u into dy dz. Assign it as equation A. Now, the next step is we have to find the mass of fluid entering EFGH per second. The mass of the fluid entering EFGH per second. You see EFGH. Take the figure and you please see EFGH. You can see in EFGH, the mass will be the mass acting in ABCD plus the mass coming over to EFGH. EFGH എന്ന് പറയുമ്പോൾ x directionൽ ABCD എന്ന് വരുന്ന മാസ് കൂടെ accumulated ആകും. That is, the mass in EFGH will be equal to the mass present in ABCD plus the mass which is coming over to EFGH. You can see ABCD എന്ന് പറയുന്ന ലെഫ്റ്റ് സൈഡിലെ ഫേസ് ആണ്, but EFGH is present in the right side and you know the mass is flowing over to here in x direction. You can see the mass is coming over to here. So EFGH എന്ന് പറയുന്ന ഫേസ് കൺസിഡർ ചെയ്യുമ്പോൾ ABCD യിലെ മാസ് കൂടെ accumulated ആകും in x direction. In which direction? You see what is the direction over here? It is in x direction. So what happens? The mass of fluid leaving EFGH per second is equal to, I told you the mass of fluid in ABCD also get accumulated. So it becomes rho u into dy dz plus, what is this term? Rho into u into dy into dz. This is the mass of the fluid entering the phase ABCD. ABCD le മാസ് ആണ് റോ ഇൻറ്റു യു ഇൻറ്റു ഡി വൈ ഡി സെഡ്. അത് കൂടെ അക്യുമുലേറ്റഡ് ആകും ഇ എഫ് ജി എച്ചിൽ വരുമ്പോൾ. ഓക്കെ, സോ റോ ഇൻറ്റു യു ഇൻറ്റു ഡി വൈ ഡി സെഡ് പ്ലസ് see what is the mass in the phase EFGH. അവിടുത്തെ mass എന്ത് വരും? Rho into again u, because we are considering the velocity component in x direction. So rho into u into rho AV അല്ലേ, so rho into velocity u, velocity component is u, so rho into u into the area. What is the area? dy dz. You see what's the area here? It is dy and here it is dz. You see this is dz and this is dy. You see this is dy and this is dz, and the velocity component is u. So rho into u into dy into dz, and it is changing with respect to x direction. So it becomes dou by dou x of rho into u into dy into dz. So the mass in EFGH per second can be written as rho into u into dy dz. That is mass of fluid which is entering the phase ABCD plus rho into u into dy dz. That is a mass which is present in EFGH in x direction. That is, it is changing over x direction. So we may write it as dou by dou x of rho into u into dx dy dz, that much into dx. Okay, now assign it as equation D. Assign it as equation D. Okay, now what will be the gain of mass in x direction? The gain of mass will be the difference between equation A and equation B. So the gain of mass will be, I told you, gain of mass, how can we find the gain of mass? It will be the difference between equation A and equation B. Now, gain of mass in x direction is equal to A minus B. So you substitute equation A and equation B. So rho into u into dy dz minus rho into u into dy dz minus dou by dou x of rho into u into dy dz into dx. So the first term and second term, one is positive and next one is negative, so it get cancelled. So what's the remaining term? Minus dou by dou x of rho into u into dy dz into dx. Then we can write, simplify it as minus dou by dou x of rho into u into dx dy dz. Okay, you are just opening the bracket, that is rho into u into dy dz dx നെ rho into u into dx dy dz എന്ന് എഴുതുകയാണ്. Okay, so this is in x direction. X direction minus dou by dou x of rho into u into dx dy dz എന്ന് കിട്ടിയത്. So what will be it in y direction? What will be the gain of mass in y direction? X direction minus dou by dou x of rho into u into dx dy dz എന്ന് obtain ചെയ്തു. Then what will be the gain of mass in y direction? It will be, what will be the change? Minus dou by of rho into v into dx dy dz. Why? Because v is the velocity component in y direction. Y direction velocity component is v, so it becomes minus dou by of rho into v into dx dy dz. Then what will be the net gain of mass in z direction? Minus dou by dou z of rho into w into dx dy dz. Why w is coming over there? Because w is the velocity component in z direction. Now, what will be the net gain of masses? Net gain of masses means it will be the sum of these three. Minus dou by dou x of rho into u into dx dy dz plus minus dou by of rho into v into dx dy dz plus minus dou by dou z of rho into w into dx dy dz. and we take the minus sign outside and you take dx dy dz outside. So it will be dou by dou x of rho u plus dou by dou x of rho v plus dou by dou x of rho w. As I did as equation 1. Then you know, have learned in physics, the mass is neither created nor destroyed in a fluid element. The mass can neither be created nor be destroyed. So the net increase of mass per unit time in a fluid element is equal to the rate of increase of mass in that element. Okay, we can equate this to the rate of increase of mass. You see, the mass of fluid in the element, can be represented as rho into volume. That is, mass is represented as m. So, rho is mass by volume. So, mass by volume into volume and remaining term and the mass of fluid in the element എന്ന് പറയുന്നതിനെ m എന്ന് represent ചെയ്യാം. Okay. Now what is rho? Rho is mass by volume. So mass by volume into dx dy dz എന്താ അതും volume ആണ്. So mass by volume into volume. Volume and volume will get cancelled. So the remaining term is mass only. Okay. So ഇതിനെ നമുക്ക് എന്തെന്ന് എഴുതാം? Rho into dx dy dz. What is dx dy dz? അത് volume ആണ്. Then what is rho? Rho is a density. എന്ന് വെച്ച് കഴിഞ്ഞാൽ ഇത് mass by volume ആണ്. Then dx dy dz volume ആണ്. So മാസിനെ തന്നെ mass by volume into volume. We are writing mass itself as mass by volume into volume. So that is how we represent mass of fluid. Mass of fluid we are representing it as mass by volume into volume. So mass by volume is rho. Then volume is dx dy dz. Then it is increasing in that particular period of time. So we have to differentiate it with respect to t. T is a time and it is increasing over t. So we have to differentiate the same with respect to time. So dou by dou t of rho into dx into dy into dz. Now, what is the equation 1? You equate 1 and 2 because according to the principle of according to the theory of continuity, the mass is neither created or nor destroyed. So we can write the net mass is equal to increase in mass per unit time. Okay, the net mass we have obtained in equation 1. All of you see equation 1. The net gain of mass is represented in equation 1. This can be made equal to the mass of the fluid in the element. In net gain of mass, it will be equal to the mass of the fluid in that element. So this will be equal to the mass of the fluid in the element. Then how the mass of the fluid in the element can be represented? M can be represented as m by v into v. So what is m by v? Density. What is v? Dx dy dz. Then there is increase of mass with respect to time. Okay, it is increasing with respect to time. So we may write it as dou by dou t of rho into dx into dy into dz. Now you are equating 1 and 2. So what happens? What's equation 1? Minus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. That much is equal to the mass of fluid in the element. That is dou by dou t of rho into dx into dy into dz. From this term, you can take the rho outside. So it becomes dou by dou t of rho into dx into dy into dz. Then in the first term also, in equation 1, there is dx dy dz. So both of that terms get cancelled. Now what's the remaining term? Dou by dou t of rho plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. Nothing, it is we are just cancelling dx dy dz. Only that is the change. You do together with me, so it will be easier. Now equation 3 represents the continuity equation. Now for steady flow, okay, equation 3 is a continuity equation. Now we can consider some cases. Case 1, if it is a steady flow, if it is steady flow, rho will be constant. So what happens? For steady flow, we may write the continuity equation as rho is constant, so this term disappears. So dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. Then for incompressible flow, rho is constant. So what happens? The term rho vanishes. So how the equation changes? Dou by dou x plus dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Next is a three-dimensional case. Two-dimensional equation. That is, for two-dimensional equation, the term z will be absent. So dou u by dou x plus dou v by dou y equals 0. Once more, that is, finally you obtain the continuity equation as dou by dou t of rho plus dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. Okay, that is your continuity equation finally. Now, if it is a steady flow, for steady flow, density is there is no change in density with respect to time. That is, we can say dou rho by dou t is equal to 0. Dou rho by dou t is equal to 0. So for steady flow, what happens? If rho is, this term is equal to 0, what happens? Only the remaining three terms will be present in the equation. So you can say equation 3 converts to dou by dou x of rho u plus dou by dou y of rho v plus dou by dou z of rho w. That is, the first term vanishes. Then, if it is an incompressible flow, we have talked about incompressible flow, that is, density is constant there. So what happens? The first term vanishes, and from the rest of the terms, rho vanishes. So how the equation changes? Dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0. Okay, that is incompressible flow. Next is two-dimensional equation. For two-dimensional equation, the z component will be absent. That is only x and y component. We are considering only x and y component. So what happens? Dou u by dou x plus dou v by dou y will be equal to 0. Okay, that is about the continuity equation derivation. So we have to learn the continuity equation in three dimension. Okay, this is in the first case we are just representing the continuity equation, but in the rest of the portion we are deriving the continuity equation in three dimensions. Okay, it is very important. So all of you should learn and similarly do it in your notebook. Okay, thank you.